Hi everybody, it's Rob here from heatengineered.com. We've had a lot of questions and a lot of requests for this video on how to use our pipe calculator, and I'm going to spend half an hour or so just running through a very simple one bedroom flat calculation that you guys can do, and to show you literally how very easy it is to do, as long as you stick to some very simple three very basic principles, which I'll get into as we move forward. Now, there's a couple of things that you need to do. Obviously, you get your room by room heat loss calculation, and most of you know that you're up here on step 9 of the calculation, and you can see if I just zoom in there. Now we've got a total heat loss on this small one bedroom flat. It's an older flat, it's a 1980s built flat, 4.4 kilowatts, and when the external temperature is minus 2.3. So again, you kind of it's a very low output heat pump that we're going to be putting into this on a DT5 circuit. So we've got to calculate the pipe work that's there. Now you can do one or two things. This could either be an existing system that you've drawn out, or you could design it from new. It's entirely up to you how you want to work this, and we'll discuss both ways of doing it. And this is whether this has got microbore in a section there or whatever it is that we've got. And if I zoom into this drawing here, I mean, you don't have to do any drawing as neat as this. The only reason that I've done a drawing like this is just so that it's easier for me to explain the methodology, if you like, behind calculating out index circuits and obviously your pump sizing or fundamental pump sizing for all your pipe work, etc. So all you need to do really is, if you're in an existing building, is just get an A4 bit of paper or a back of a packet or whatever it is and just simply draw out a basic layout of what you've got. Use thermal imaging cameras if you can't see any pipework under floors, and they should show up if you run the heating system, those sorts of things. So you can just get an idea. And all we're trying to do is, I say this all the time in courses, and we're just trying to get closer to the truth. So I know that I can pace out, and I can walk about a meter in a pace, so I'll just pace that out. So that's four and a bit meters between that point there, that T section there. There's a drop coming downstairs, so I know there's a T piece there, and I'm just working out. I can see there was a bit of 22 mil pipe coming out of there, or a bit of 15 mil pipe coming out of there, running to those 3 rads, and you can just pace it out and just see what you're going on. But you can see radiator pipe work coming out of the floors. All sorts of things like that, so you know roughly what size of pipework is going to be placed there. So as I say, all we're trying to do is get much closer to the truth. That's on an existing circuit, and I bet you, everybody that's listening to this now, that you will see, and pretty much every single pump that you see is massively oversized. In fact, there's an incredibly frightening statistic that I heard from the guys at IMI Hydronic, and this has been bona fide many times. Between 15 and 20% of the entire world's electrical energy usage is taken up by dead-headed and oversized pumps, or dead-headed or oversized pumps. I mean, just think about that for a moment. You 15 and 20% of the entire world's electrical usage is taken up by dead-headed or oversized pumps. That's trillions and trillions of pounds in wasted energy if that is the case. It's something that I think is, as I bang on about for an awful long, as many years as I can remember. I'm sure I get on people's nerves. This is we live in a wastage crisis, and this kind of exemplifies that, exactly that. But anyway, moving on. You can see over here we've done our room by room heat loss calculation. We're at step 9. We've got 4.4 kilowatts, and as most of you know, that then is your total watts that are required in there. There's your 4.4 kilowatts in total, of 4,400 watts, and then for each room there's your bits and pieces there, so that's put up there. So whenever you draw out a hand drawing, what I'd always say, you can see that the kitchen there is needing 1,044 watts. So we go to the kitchen and just write it down as to what it is on there for that, and all your distances. Now there's a couple of things that you need to know when we're doing this, which are the difference between circuits and sections. Now with circuits, you can see that from your primary heat source here, let me just zoom into that just a little bit there. So from your primary heat source going out, so you can see that running out this way there, all the way out there, that's one circuit. So that circuit there, we call that A. We then call, I zoom out a little bit so you get a full picture now because you can see what's going on. Your primary circuit running right the way out there to rad 6, that's circuit B. You can name them what you like, it's entirely up to you. Or that one running down there would be circuit C. But there's another thing in there, and I'll show you this. I've done some drawings on this to show you and highlight it properly, so you can stop the video whenever you want if you're just taking your time to learn all these things. But you can see that what I've done is here I've added different measurements in, so you can see that from the primary heat source running out to T1 there, that's a section. So that's your primary section. And you can see I've just added there 1.5 meters from that going up into the ceiling of this property. And then there, from the T1 running out to rad 4 there, you can see I've put in 3.5 meters in total for that. So that is your section running out there. So that's another section there. There's another small section just there. There's another small section just, well, it's not a 4.5 meter length, but that's another small section there running out, and then another section going out to that rad, and then another section going out to that rad. So whichever which is upstream, whichever way you're coming from upstream, you always go to the far side of the radiator to measure that section. So the far side of the radiator to measure that section, like that. If the flow was coming from the other way, it would obviously be that section, and then the other side of the rad down that section there. So that's just some fundamentals things of working out what the difference between circuits are and sections. And obviously, you could have another drop there, you could have another T-piece coming off of there for some rads over this side or whatever it is, and you just name it. So that might be circuit A, that will then be B, and then C and D and E and F and whatever it is. And obviously we're saying that, with this scenario, you got up to 26 circuits, obviously with the alphabet. But we can start labeling them all sorts of things. It could be, Z25/B or something like that, if that's how you wanted to do it, and you've got loads of different sections. So it doesn't matter if you're doing a 6-bedroom, 6 radiator system like this one is, this little system, or a 600 radiator system. It makes no difference. You just got to do one section at a time. So I'll come on to the principles that you're going to need to learn in a second in order to make this tool really, really easy to use. But there's a few little things that we need to just go through first of all, and just to make sure that we've got everything calculated out correctly. Now, to subscribers that are existing at the moment, you know that when you get to this stage at page 9, you need to select your heat source type and model to proceed. So we click on that, and this page drops up. So we've got an air source heat pump. We're choosing Panasonic for this one, and the reason that we're going to choose this one is I'll show you now. We've got a facility now where every manufacturer, and you can see we've got hundreds of them, dotted around. There's literally hundreds of them on here. We've got loads and loads of manufacturers, but not many manufacturers are very interactive with our software at the moment, and I think a lot of manufacturers don't realise that the account they can have is free of charge. Well, Panasonic have taken good advantage of this, and I know they get good business from it. But the crucial point is that from their particular drop-down menu of all of their heat pumps and everything that they've got there, we've chosen a little 5 kilowatt unit to suit this. But the point is that they've updated all of the SCOP data and everything like that within these units as well. So you can view the image of the heat pump itself. But more importantly, you can actually view the PDF, because we are at -2.3, I think we said. Let's just cancel that a second. So we're at -2.3, so 4.4 kilowatts at -2.3. That's all the building is going to need when it's at -2.3. So we've got this unit, but we need to find out what the output's going to be when it is -2.3 outside, and that's how you would put in the design capacity for your domestic hot water. So if we look at that and we view that PDF, Panasonic have done a great job here. They've added that up there. So if we zoom in just a little bit there, you can see at -2.3, we're going for a 45-degree flow temperature on this. But -2.3, we're about 4.91, 4.90 kilowatts is what your output's going to be. So that's great for us. That's a bona fide output which we can put in this, and gets us, as we keep saying, is becoming a little bit of a saying, we're just getting us closer to the truth as to what the actual heating system itself is needing. So we're happy with that. So we click OK. Now we know we can work well. So we now go on to our optional pages, and we go to our pipe and pump sizing. And here we go. Right, so there's a few things that we need to look at when we get it. So we've got a load of parameters here that we need to work through, and I'll just work through these as quickly as I can, just so you get an understanding. I've been designing systems pretty much all my career, that spans just over 4 decades now, and I've always designed everything at 1 meter per second. And every hydronic designer I've ever spoken to, they all agree that 1 meter per second is the is the gold standard. CIBSE state between 0.5 and 1.5 meters per second. And the reason that we don't go over 1.5 meters per second is because you then start to get system noise, you can get system erosion, you can get component failure, all sorts of things like that. So it's really quite important. If we can get to around 1 meter per second, that's great. And also with 1 meter per second, that's a kind of perfect velocity that you won't get sediment sitting in radiators and pipe work and blocking up things if you've got, you know, a poor water quality management, which I'd hope most good engineers wouldn't have now. So we've got the minimum velocity stated at 0.5. CIBSE also state that the maximum, or sorry, the optimum pressure loss across a system is around 300 basically, and they do state it's between 300 and 500 pascals per meter. But again, if you're looking at individual systems, or existing systems like this, or if this could be a new one, it doesn't matter. You can make your decision as to what pipe sizes you want to choose, and we'll exemplify that as we move further through this tutorial. I'm going to stick with 300. That's always a good place to start. We've also got your difference in fluids. So we've got water, and we've got water and glycol. Not sure how many people are using glycol these days, for the simple reason that if anybody's done either my course or the Heat Geek course or Kim's course for the Heating Academy Northampton, done those courses, you'll know that the specific heat capacity of water changes quite considerably when you're adding 25% or so of glycol, and it drops it down to about 3.7 as opposed to about 4.2. So you get it's thicker, if you like, and so it's harder to pump around. So your pump running costs, etc., do change. So a lot of people are using antifreeze valves, or sometimes even not at all. But that's the basic. I would stick to with water. We've got our pipe type here. Now, what we are going to be adding on in version 2, which is being beta tested as we stand now, we will be adding some more pipework options. Certainly copper table Y will be added, which is obviously your soft copper for a lot of microbore systems that are existing. And I want to try and prove in this tutorial that a lot of low temperature designs, whether it's a heat pump or a boiler or whatever it is you're changing to do, and you're trying to run at, you know, high flow, low temperature. So instead of using a DT20, so a difference in temperature of 20 degrees across a flow and return, we're going now more to a DT5. So we're quadrupling the flow rate running through. But I want to try and prove to people that even microbore soft copper will work fine on these low temperature, high flow systems. So, you know, a lot of the pipework that we've got is quite oversized, but we'll play around with that as we go, and we'll see. Any suggestions that any of you guys have got that you want to add on different pipe types, please let us know. We'll get hold of the technical data, and we'll get them added as we move forward with version 2. As I say, this is built by you guys, and we do what you ask. Select your units for pressure loss. Now, I know this is what Kim likes to use, millimeters H2O from the Heating Academy Northampton. I quite like to use pascals per meter. The reason being is that there's 1,000 pascals in a kilopascal, which makes it around 1,000 times more accurate, if you like, or it's just a few more decimal points. And again, you've got your litres per second, or that I prefer litres per second. And just to point out, you can just see here where we've got here this mass flow that says kilograms per second. A kilogram is exactly the same weight as a litre of water. So a litres per second is exactly the same as kilograms per second. So if anybody didn't know that, you do now. We've also got within the system, because it's quite a big calculator here, we've got more columns here which we can add onto the system. So I'll put it all as full on, and we'll just move around this as we go. So there's 3 fundamentals that we need to do. Well, actually, let's just before I do that, let's just show you these 2 drawings. So what is a section? This is a little help section that we've got here. So a section, and you can see on that, that's another copy of this drawing here. So there's a section there, so between the primary and T1. So that T piece there is T1. There's another section there from T1 out to rad 4, so all the way out there. There's another little section there, just of that little ½ a metre, you can see, that runs at that point there, and we'll calculate these out in a second. Another section there, another section there. So that's what a section is. And then a circuit, as we've just discussed, is simply that. So that's circuit A running out there, circuit B running out there, circuit C running out there. You could have, however many circuits that you want to have. This is fundamentally just for as a tutorial and an example. So first thing we've got to do is we can start wherever you want. It doesn't matter where you start. You can start on that little 3 metre long section there if you wanted to, as long as you remember what you've done. So all we've got to do, there's 3 fundamentals here, 3 fundamental points with calculating any index circuit wherever you are. And this is what I want to try and make it as simple as possible and not get guys confused. So if we start from our heat source, we've got a primary flow and return that runs up to T1. It's 1.5 metres long. Let me zoom in to that, and you just get a little bit more clearer picture of it. So it's 1.5 metres long. Now we know that that is going to be taking all of the energy for all of those circuits. So for all 3 circuits, that primary pipework is taking for that rad. So it's every rad, that circuit there and that circuit there, it's taking everything. So we know that's the full heat loss of 4.4. So you can see we've put in here 4.4. Now that has been dynamically put through from the heat loss. So that's all good for us. We've chosen whether we're having water, we've chosen our flow temperature at 45 degrees. That makes our specific heat capacity change to 4.18. Now, specific heat capacities do change somewhat from the lower the flow temperatures you go, the lower the specific heat capacity number. The higher the flow temperature you go, the higher the specific heat capacity number. All right. So as it's a calculator, we might as well get as accurate as we possibly can. I know when you're doing longhand, most people will just round up to 4.2, and that doesn't matter with domestic circuits. The only time I would say that there could possibly be a difference between, say, 8mm and 10mm copper is that specific heat capacity number, and that might make your decision on whether you can stick with a piece of 8mm or whether you've got to lift somebody's floor up and actually start replacing pipework. That could either win or lose you a job. We're going for 45 degree flow temperature here. We've got a DT of 5, so it's flow temperature 45, return at 40. We know that in this existing system here, we've got 22mm pipe, so we've clicked on 22mm pipe work, and you can see it's been accepted as our velocity check because we're under our 300 pascals per metre, and that's given us 271 pascals or 271.7 pascals per metre. Now, there's 2 things you need to know. Obviously, how much energy is that section of pipework taking, which we've just covered. We've then got to know, the second question is how long is that pipework? Now, this is a flow and return pipework, which is 1.5 metres up to that T1. But because it's a flow and return, we've got to double it up. So that is 3 metres. So the pipe run, flow and return, is 3 metres, which you click on there and you put in what you like. Now this section is, you then, the third question is how many changes of direction does that section have? Now this is obviously up for debate. I'm just going to explain to you that this is the way I've been doing this for as long as I can remember. CIBSE state a standard when you're adding fittings. You can see just over here when you're adding fittings onto a pipe run. CIBSE state as a standard you would add 50%. Now I personally take a little bit of a challenge at that, or I challenge that, and I think that we are wasting residual pump head with that, of allowing that much, and that is oversizing our pumps. I say this, and again this is only my opinion, but I say in the hundreds and hundreds of heating systems that I've designed and installed over my career, I will only ever add, literally, for every one change of direction. So you've got 2 pipes coming up the wall there, but they're both changing direction to go down to that radiator there. I class that as 1 change of direction, okay? And I would say that for every 1 change of direction, you add 10%. So if that going out to that radiator there, so there's no change of direction at that point because we haven't changed yet. We're only changing once we've gone into another section, another bit of pipe work. We've got 1 change of direction there. We've got another one there, and we've got another one going up into the rad. So that would be 10, 20, 30% of extra residual or resistance. So we add on that 30% into that. And what I do is if it goes up to 5 changes of direction, that's your 50%, and then you stick with the Sibsi equation of 50% thereon if there's more changes of direction. And that just gets you a little bit closer to the truth and gets your pump calculation and your pump sizing just that little bit more accurate. So that's that done. That's that first section there is done. All right, complete. So anything that's in orange, you can see this is what you have to fill in. We've then got our section A1. So I've just pre-populated these before we move on to the next slot. So we've then got this section running out. We know that is in 15mm pipe work. So we can look at it there, and it's carrying. So you've got so the first question that we ask is how much energy is that carrying? All right, and we can see that on the room side of it is 678.51. So 678.51 watts is what that's carrying. Now I went through here and you can see that I've got 705 watts written down here. If I select on that, what we've got to do, we've got to see, because I was sizing radiators within the things. So this is the bedroom one. Yeah, and bedroom one is here. I was sizing radiators, and the closest I could get to the output that I needed was 705 watts at 42.5 degrees mean water temperature. So that's obviously the mean water temperature between the 45 degree flow temperature and the 40 degree return temperature. We don't have to do that. We can untick that, and we can just tick the room if that's the case, and that gives us our output that we've just asked for here. So let's just stick with the rooms then for now, because that's kind of what we need. So we click OK, and you can see it's changed there now, 679, which is correct, it's rounded it up. 45 degree flow temperature, 5 degree delta T, so 40 degree return, and 15mm pipework. We've then got 3.5 meters from that T piece running right the way out to that rad, and you'd always go from upstream. You'd run out to the furthest side of the radiator and have that as your linear length. Okay, so we times that by 2 because it's a flow and return, which gives us our 7, and then we add on there our 30%. Now that, when you think about it, is that circuit done. That circuit A is complete. So we come back over to this side and we create a circuit. So we've got our primary, which is there, and we're also adding in A1 because we've called that A1. It's going out there. So we click on that and we press save. And there's our first lot that is there. So we're into pascals. Okay, so you need to just change those values up there, and you can see that we've got 1693 pascals from that section there right the way through to that on the pipework only. Obviously you need to find out what the pressure loss is of the heat exchanger within this unit, and obviously again with any hot water cylinders that you might have, which you can then add on to find out what the index circuit actually is. But don't forget, whatever the pressure loss is of this ground source heat pump, that gets added to every circuit that you've got because it is common to every single one. So we're now looking at adding another section, because we're now going to do this section here. But now we've come out away from circuit A, which was there. We're now part of circuit B. So this small 1/2 meter section of pipe here, we're going to call that B1. So if we add a section and we click on that and we call it B1, we now got to ask our second question is, how much energy is that taking? Well, it's taking everything. If I click on that and zoom out again, it's taking all of those 5 radiators, or actually I'm going to just make this 1 radiator when we move forward, but it's taking all of those 5 radiators, or 4 radiators as we're going to say, all right, and lose that one. So all we've got to do over here is not taking bedroom 1, as you can see. So we leave bedroom 1 out of it, and we'll put in the kitchen. Oh, sorry. So we've got the kitchen, the lounge, missing out the bedroom. We've got the landing, and we've got the bathroom. So we've got 3.7 kilowatts just down there that it's taking. So we click on that. There's your total. You don't have to keep typing in the 45. I mean, we can do that this time. What you can do, you can just simply copy all. So you just click copy all, and there's a DT5, and that's it. There. Oh, sorry. Copy all, and DT5 in blue. And that joins that straight up there. That section of pipework there is also going to be 22mm pipework. And again, that's accepted. There's your pascals per meter at 202. We've only got, if I zoom in again, we've only got 1/2 meter in length, but I'm going to zoom right in there because I just need to make sure that people understand this a little bit there. So we've got 1/2 meter in length, so which we add together because it's a flow and return, so we make that 1. So we're on 1 meter in total. Now, how many changes of direction have we got there? So if you look at that closely, if I zoom in even more, you can see you've got a T-piece and then you've got a street elbow in it, because you've never seen a T-piece look like that in a corner. So just bear in mind of those sorts of things there. So we haven't changed direction there at that point there, but we've got those two there. So it's 20%, not 50. So we're already saving residual pump head by dropping down from the CIBSE standard and getting a bit closer to the truth. So 20%. And then there's that section done. We can then add another section, which in B, which is going to be this section from T1 there out to rad 5. And you can see it's 4.3 meters long. So we add a section down here, and we're going to call that, if we had that one as B1, we're going to call this one as B2. So we click on that and we say B2. And then we say to our second question, how much is that section carrying in terms of energy? Well, it's carrying all the energy. That one section of pipe is carrying all the energy for radiator 5 and for rad 6. So it's taking all of the bathroom and the landing. So we just come down here now and we just click the landing, which is taking, and the bathroom. And that's it, 1.355 kilowatt. I think everybody's beginning to understand how easy this is to use now. Again, a flow temperature, so we copy it all, 45, copy all, 5, DT5. And then down from there, let's just go in there. Let's just say I don't know, let's just put 15. Let's put some 15mm copper in there. Okay, we could drop down the size there. So this is the scenario that we've got 228 pascals per meter there. But that could be smaller. I don't know how low that could go. You might get away with 12mm. Let's have a look. Yeah, 12mm gone up a little bit high. So 15mm is probably pretty perfect for that pipe sizing. But again, you can make engineering decisions on this, and I'll go into a bit more detail with that in a moment. So we had 4.3 meters long, as you can see. So we've got to double it up, and that makes it 8.6. So there's your pipe run there at 8.6. And click OK. And how many changes of direction have we got? Well, there's nothing through that T piece, that's just straight through. But there's one going up into the radiator there. So again, we beat the CIBSE guidance, or we try to. I'm not saying CIBSE are wrong, they're just covering it, the whole thing. So we just got 10%, one change of direction. So we're now saving even more energy, is the point. So then we've got the next section we've got to do is this last section is 2.5 meters long on circuit B. So we now add another section, and of course this one now, that's it. This one now is going to be called B3. So we click on there at B3, and we say how much energy is that taking? Well, it's only taking the energy from the bathroom now. So all we've got to do is just click the bathroom and add that, and job's done. Again, 45-degree flow temp, copy all there, DT5, and again we've got 15mm copper serving that. I'll tell you what, let's go down. Let's put a bit of 10mm copper in there and see what happens. Yeah, see, that's a little bit high because what would happen there is you've got 772. Now, if that was existing and you couldn't change that pipe work, would it still work? Well, what's your flow rate on there? So your flow rate, so I'm just trying to find where I'm at now. Yeah, so your volume in litres per second, I mean, you're still low. It's very, very low. So you could, I mean, that would work. And don't forget, 772 pascals. One of the smallest pumps you can buy on the market is like a 2040 pump. So 20 mil bore, 40 is 40 kPa or 40,000 pascals. So you think that's one of the smallest that you can get. But you'd have to go, because that's 2.5 meters from that point there to there. You'd have to double it up so it becomes 5. So it'd be 772.2 times 5. Plus your one change of direction, which is 10%. So I'm not going to go with that. I think we're going to change that, and we're going to put it in as 15 mil, as was stated. We've then got our 5 meters of pipe run in there, and again just one change of direction. So we just change that down to 10%. I'm pretty sure everybody's probably got this now of how easy this system is to use, but that is now circuit B is completed. So what we've got to do now, if I just zoom out, oh sorry, if I go across it now, we've got to now create circuit B, because you can see we've created circuit A there. Let's create circuit B. So we've got that. So we've got our primary flow. We've then got B1, because we don't have A1. We're not going down this section here at all. We're just flowing down here. So we lose that one there, and we start B1, and we've also got B2 there and B3. So we have that, and we save it. And there you go. So we've now got 4,000 pascals, yeah, or 4 kPa. And the smallest pump we can get is 40 kPa. I think they do a 3 meter head pump, which is a 30 kPa. But you get the understanding. There's not a lot of pressure loss on this, and these are are relatively small pipes. So, and it would work if we had the if we'd have changed that, and we'd have had that at say 12 mil or 10 mil copper running through that. So that's that section. So we now need to add another section, and we're starting from here. It's just these last 2 sections just to do. So if we add a section, and we're now going to call this, because we're on circuit C, we'll call this one C1. So click on that, and we call it C1. And how much energy is our second question? How much energy is that section taking? Well, it's taking the energy of that rad and what is going to be just one rad here, but I'm going to just join these up in a bit. Okay, so we're taking the kitchen and the lounge. So that's that bit of pipe work there is taking, that's the whole lot. So we'll click on the kitchen, that total, and the lounge. Click OK. Job done. Copy all again to that, copy all again to that, and on this section going down here, let's do it in 15 mil. Let's do a 15 mil drop, and let's see what happens, because this might be quite a high pressure loss with the amount that's going down it. Yeah, it is, but what I'm going to do is I'm going to carry on, because we've got residual head. You know, the Sibsey state between 300 and 500 pascals. We're 100 pascals over. So yes, it is higher and it's outside of our design parameter, but that might be existing. It might even be buried in the wall or whatever. You don't know. This could make or break you winning or losing a job if you've got to replace all of this pipe work down here. And sometimes you will not have to. So how many changes of direction has it got? Well, we're changing direction there. We're changing direction there, and we're changing direction there. So there's 30%. So again, we save 20% of residual head, and we change that to 30%. So you can add in what you want here. This is purely to calculate, so I'm not telling you what you should do. But it's 4.5 meters down to that. So again, we're upstream, so we come down to the right-hand side of the radiator. If the flow was coming in that way, we'd go to this side of the radiator. 4.5 meters, flow and return, so we double it up, and that becomes 9. We click on that, and that's 9. Job done. And then the last section that we've got to do is just to this one radiator out here. And I think what we'll do is we'll call it, this is just the one radiator heating this room. All right, so what we'll do, we add another section, and we're going to call this C2. So that's from that point there out to there. So it's C2. Click on that, C2. And how much energy is it taking? Well, it's just taking the energy from the lounge, isn't it? So we've just got to add that. So it's 1.3 kilowatt. Click OK. And there it is. Let's just copy all again and just get our flow and returns in into that. And let's just put that in as 15 mil as well. There you go. How long have we got? So we've got 3 meters in length, plus that 1.5 because the rad's moved down. So we're getting rid of that there. So that's 4.5 meters. So again, double it up and we got 9. So we click on that 9 again. And we're there. And how many changes of direction have we got? Well, there's nothing going along there. There's just one going up into the rad. So again, we're dropping down from the standard 50% and we're taking it down to 10% because it's one change of direction. And that's it. We're done. So we've just got to create this last circuit. So circuit C down here. So we create circuit and we choose what we're going to be using. So we go back to our little hand drawing that we've done. And we decide, right, okay, so what is going to be in this circuit? Well, the primary obviously is in it. B1 is in it. A1's not, but B1 is in it. B2 is not in it, and neither is B3 in it. But C1 is, and C2 is. So we just click on C1 and C2, and we save it. And then, voila, you can see there, section C has now been highlighted as the index circuit at 10,505 pascals, or if we want to change those pressure losses, so 10.5 kPa. We know the smallest pump we can buy is around 40 kPa, so something along, I think there is a 30 kPa pump out there, but you can just see how massively oversized most of these pumps are, just for a standard 1-bedroom flat. Again, you can change any of these things to millimeters if you want, so it's just over a meter of head, as you can see, just there, which is the whole thing. So I prefer pascals, but then everybody can have their own view. Now you can see down here we've now got our scenario for our pump sizing. Now, as we mentioned earlier on, this is not adding in at this stage. In version 2, which is going to be launched in the next couple of weeks, we will have another section on here which is saying what your primary heat exchanger is, on whether it is your boiler or your heat pump or whatever it is that you've got. If you've got a plated heat exchanger or a secondary heat exchanger, some hydronic separation, whatever it is, if you've got additional pressure losses within those, you'll need to refer to your manufacturer's instructions or speak to the manufacturers and find out what the resistance ratings are of those heat exchangers, and then you add that to the total amount of pascals that you get within your primary circuit. All we've got to do is calculate this index circuit, and as I say, it doesn't matter if you've got 5 radiators or 5,000 radiators. The index circuit could be the radiator or valve or other fitting that's right next door to where the pump is. It doesn't have to be a million miles away for it to think that. So it's a wrong thought to be thinking that the index circuit is the furthest point away from where you're starting. It's not. It's whatever got the highest resistance of valve or circuit within the system. Once you can get over that resistance of that one circuit, it will get over the resistance of all of the rest of them. That's the whole point. I try and describe it when I'm teaching this as this method. If you imagine a 1 meter length of 28 mil pipework, for argument's sake, or a 1 mile long length of 28 mil pipework, and right in the center of that pipework, you've got a 28 by 28 by 15 millimeter center T, and and there's a bit of 15 millimeter pipe that sticks up vertically from that bit of pipe laying on the floor. I'll just say 1 meter. It sticks up in the air 1 meter. The 28 mil pipe is capped one end, and it's connected the other end to a pump and to a brake tank of water, for argument's sake. Now, if you imagine that bit of 15 mil pipe that's in the middle of that, or teed into the middle of that 28 mil pipe work, and then 2 inches either side of that 15 millimeter pipe work, there's another T piece with the same amount of 15mm pipe sticking in it, but it only comes up, say, I don't know, 950 millimeters. It drops 50 millimeters each time, but you keep adding T's all the way down, so you create this kind of pyramid shape of pipe work going down either side, right the way to the end. As I say, it doesn't matter if it's a metre long or a mile long, it makes no difference. What you realise is that as long as you pump enough water to get it out of the tallest bit of pipe work, in other words, the bit of 15mm that's a metre long, you know that however many pipes you've got coming either side of that are lower, it's going to come out of those, because it's coming out of the one that's at the top. That's your index circuit. So that's all you've got to think about in the terms of index circuits. That it doesn't necessarily mean it's the furthest point away. But anyway, we've now got this pump sizing there, and we're telling that our pump is telling us that we now need 765 litres an hour. Again, we can change these flow rates if we want to into whatever we decide that we like. Doing it by hour seems to be the kind of way a lot of people do it. Now we are looking at getting different pump companies sitting down here as well. At the moment, we've only just got Grundfos, because we're working quite closely with Grundfos. But if you come onto this point now, you can click on this link, and it opens up Grundfos Product Centre. Now, if you want to, you can sign. It's a free sign up. I'll just sign into my account here, and we can see that it comes up now with your size your product. Very, very easy tool to use this. So we're looking at our application. Okay, so we're looking at an application. We're looking at domestic buildings with this one, and we're looking at our domestic heating. So we now have got our basic parameters that are stuck in. We're looking for the main circulator pump for the domestic building. So we click on that, and we now get our parameters that we've got to set in. Now we decided we're going to use litres per hour. And if we go back to our summary, we needed 765 litres an hour. So let's call it 770 litres an hour. So we go 770 litres per hour. And then I like to work in kPa with this, and we've got, as we look back down here, if we go, this is 10,000 pascals. If we change that to our kPa rating, we've got 10.5. So let's give it a little bit of leeway, and let's just put in there 11 kPa. So we're just about the right size now for what we've got on that particular unit. So if we click Start Sizing, it should come up now with a list of 8 best matches. And there you go. So it's a standard Alpha 1 look 1550 pump. I'd be careful at the moment, because you can see these orange. I presume that means on this stock indicator that these might be harder to get hold of. I would think. I mean, the Alpha 1 is generally fairly well available, but I would check with your supplier and check with your manufacturer first of all to see what's going on. But if we just choose this one for now, we know that's going to be correct. We'll click on that product, which will now load up. My internet is being a little bit slow for some reason. And then you come up with this unit, which is there. Now we can see that we've set up our parameters look, which is our 800 or so, sorry, 775 litres, sorry, 770 wasn't it? Sorry, 770 litres per hour, and then just our 11 kPa head there. So you can see this pump is still massively oversized for what we need to do. But what we can do now, which is a really good feature on this website, we can put in pump curve, sizing result, life cycle costs, right, etc. So we can generate a PDF on this now, which is superb, because you can actually now add this PDF to Heat Manager, which is obviously our digital benchmark system. So with all of your documents, so everything from the heat loss calculation right the way through to any pipework schematics, to pump sizing, to EPC reports, anything or schematics, manufacturer's instructions, anything that you want, you can add to Heat Manager, and you keep that. It goes on a QR code and gets stuck onto a heat pump or onto preferably internally onto a boiler or a cylinder or something like that, and that QR code could be scanned by anybody, and they will get full access to all of the paperwork, so commissioning reports, everything to do with that heating project. So a real good facilities to say looking around for an A4 copy of the MIs in some kitchen drawer somewhere that you can't find. But this produces this specification for this particular pump for this project. You can actually use the Grundfos Go Balance app now to actually set these things up, which is also quite a good idea. You can see that it's got all of the information that you need. There's your pump curves. Everything is set on there with all of your all of your set points. Your duty points are all listed. All the information on this is pretty amazing. Wiring diagrams, sizes, everything that you need on here. So really good feature, and I hope that this tutorial video gives you a really good insight as to how to use our pipe sizing calculator. Many thanks.